Hello, everyone. Thank you for joining us for another live webinar session hosted by EE Tech and All About Circuits. My name is Dale Wilson. I'll be your moderator today. Our session is brought to you by SIGLENT Technologies and is titled Using Advanced SMUs for Complex Electronics Device Characterization. Let me tell you a little about our presenter. Chris Armstrong is the Director of Marketing at SIGLENT Technologies, bringing more than 22 years of experience in test and measurement. His background spans sensitive measurement applications, multi-purpose benchtop testing, and fully integrated instrumentation systems across a wide range of platforms. He holds a Bachelor of Science in Computer Science and Engineering from the University of Toledo and an MBA from Case Western Reserve University. Following the presentation, we'll have a live Q&A session with Chris. You can submit your question at any time during the webinar using the Q&A section on the right-hand side of your screen. We will provide attendees with a downloadable copy of the presentation near the end of today's session. This will be available in the Handouts tab. Thank you so much for joining us. And with that, I'll hand it off to Chris for today's presentation.
Thanks so much, Dale. Appreciate it. Welcome, everyone, and thanks so much for joining us. Wanted to spend some time today and go through some of the, I think, tips and tricks on how to use source measure units and how they apply in today's sort of complex set of device characterization requirements, and a pretty broad set of automated test needs. So we'll kind of go through that step by step and see what we can learn about this, I think, important topic and process. We'll talk about some different instrumentation options and pieces along the way, but really gonna focus on sort of a combination of the basic things that you need to understand that are specialized to this sort of semiconductor and source measure testing. Important things about ranging and error calculation that I think come up a lot. We're going to talk in the second section there about low current measurements and low voltage measurements and the keys to getting the most accuracy out of your testing for those kind of needs. And then we'll kind of wrap up with some more complicated semiconductor device work, how four-quadrant operation among these sort of instruments impacts your measurements, how triggering synchronization can help you make certain measurements, and different ways to view and analyze this data. So that's what we're going to talk about today. And we're really going to start pretty basic with what is a source measure unit and how are we using these today. Well, when you think about it at its most basic level, a source measure unit provides a combination of voltage, current source, and in some cases an arbitrary waveform generator at typically relatively slow speeds, and combines that with an ammeter and a voltmeter, all really in one integrated package connected to your device under test. And it's really that integration that is the important and powerful piece, right? So because of the way this is set up, you can source voltage into a device, source current, you can move those values around, you can measure voltage and current simultaneously on the back end, and that allows you to calculate power, calculate resistance, and because of the way this system is integrated, typically gives you a wide range of capabilities, especially as you talk about lower voltage, lower current measurements, higher current pulsing capabilities, some high voltage capabilities as well, and some high speed capabilities in both how we move that source around, like an arbitrary wave generator, and how we move that and how we make those measurements and analyze the data. So really, in some sense, it's a combination of complex power supplies and measurement tools that really integrate for accuracy, resolution, and stability. And so that's where the real power comes, right? Because we can do that in such an integrated form factor, we're able to drive specialized test sequences for the device under test. We're able to get accuracies that you wouldn't get in other measurement systems, even with like a 6 or a 7.5 digit DMM, because the way it's set up, your power supply again, we're able to integrate it and get some advanced features. So let's take one step down here and talk about some of the advantages, but some also the tricks in how this is set up and how we use an instrument like this for complex testing. So the first thing we want to make clear is a device like this has a lot of pulse capabilities, which can really expand how you can use a source measure instrument. And we'll see that as we kind of go through the presentation and talk about how pulsing impacts low current and how it impacts low voltage measurements, especially. We'll talk about different results you get in these kind of modes. But fundamentally, a source measure unit has a DC envelope like the one on the left, and a pulsed envelope, which is typically a little bit wider in key areas. Right, so a standard SMU channel like ours would give you about 31.8 watts of power, DC power total. You might see that at the, in this case, you can get up to 3 amps DC and up to 210 volts, but you're in a stair-step configuration there. So you get that maximum 31 watts. But you can get up to 300 volt amps in a pulse mode with varying sort of duty cycle requirements. And so you're able to pulse up to an amp at 200 volts in some circumstances, or 6 volts at 10 amps. Right. So really, this is an outcome of the speed and integration here, which is what allows you to do high-speed pulsing with also integrated voltage and current measurements that expand the test capabilities. The other thing to note here is these the 4 quadrants that are marked here, quadrant 1 through 4, right? So this implies, and it's the truth is, these instruments work in all 4 quadrants. What that means is a source measure unit like this can provide voltage and push current. It can also absorb current like a load, and it can operate entirely in the negative regime, where it both applies negative voltage and absorbs or delivers current. So the ability to cross those 0 points and work in multiple quadrants really considerably expands the capabilities of these instruments and makes them both interesting for some complex devices that tend to work around 0 volts, and some important test points on a pretty wide variety of devices. So before we talk too much about how we use these instruments and where, right, I think it's worth talking about how you calculate accuracy and what accuracy really means in an instrument like this, because you've got accuracies both on the source side and the measure side, and you have a complex set of sort of ranging and calculation issues. And so I think it's always useful to spend a little time talking about what that all means and how we can best think about that. And the first step in that process is really looking at ranging, right? So let's take a second here and think about ranging accuracy and how we want to apply that. Well, you have really both, whether you're talking about a current source or a voltage source. In this context, we'll talk about current source for a second. But really, either way, you have the ability to adjust the ranging manually or automatically on on the source side and on the measure side. And so what are the advantages and disadvantages? Why might you want to look carefully at what you're doing here? Well, one advantage to having a higher source range, obviously, is broader values, right? You can move easily without changing ranges to higher current levels or higher voltage levels. This typically also implies faster settling times, right? Because they're at higher values with higher offsets. Also, you might find faster measurements work better at higher ranges, right? They have a lower derating effect for fast measurements in terms of speed and accuracy. Now, the advantages of a tight range, a lower source range, includes for current especially encourage lower offset currents. So each range has its own offset current value, and of course you get higher resolution, so you can set smaller ramp sizes, smaller deviations as you make those changes. On the voltage side, it's fairly similar, except you've got an additional factor of voltage noise that's really inherent to the system, right? And so as you tighten your voltage measure range, you tend to get lower noise as well. So it's a combination of thinking about your noise requirements, the speed you want to use in this measurement, how quickly you need it to settle, and what values you really want to use to source and measure these devices. Typically, when you use an auto sourcing range, it'll pick the lowest, tightest ranges available. That might cause some range shifting. That might cause some other offset changes to your measurements that might be suboptimal for what you're trying to accomplish on a large set of data, right? So important to kind of think about that. But how do you then go ahead and decide? So now you've got ranges you can select from, but how do you decide on a standard device, what you might want to source or what you might want to measure, right? Because these are typically kind of complex decisions. So I want to run through an experiment here, really about we're going to talk about it as a 1 megohm resistive load. So a resistor here at 1 megohm. How do we talk about that? How do we see that device? How should we best source and measure to get that to get optimal accuracy for our 1 megohm device? And so here's a brief description of sort of how our instrument would deal with it, but this is pretty standard across all source measure units, right? So typically, here you'll see that this chart shows the resistance error bands, essentially, you might get from different sourcing and measuring configurations, right? So what you see is as you go up in current, right? So it's a 1 megohm resistive test, right? So you could source 10 microamps and measure 10 volts. You could source a microamp and measure a volt. You could source lower than that, down to 10 nanoamps, and try to measure 10 millivolts, right? And so you might have device heating issues. You might have power limitations depending upon what you're actually trying to measure, what materials test you're trying to do, or what other actual megohm type measurement you're trying to make, right? And so you might have other considerations as well. But without a lot of other considerations in play, it's worth noting that in general, the more moving away from the lowest end current and lowest end voltage measurements gives you improved accuracy. So you can see here if you need to source down at 10 nanoamps and measure 10 millivolts, you end up with about a 3.5% error band here, and that goes down significantly each time you allow yourself to add more current, range up, going up 10x in current. So until you get to a 10 microamp measurement and a 10 volt or a 10 microamp source and a 10 volt measurement, which really gets your error rate down to about 0.1%. So always important to use the right current and voltage settings here to allow yourself allow yourself to get the accuracy you need. One other interesting thing about most of these source measure type units is that they tend to have the same accuracy on the source side as the measure side. So for instance, if you're sourcing current, whatever that current accuracy is probably very, very close to a current measurement accuracy on the same device. So in theory here, you could source voltage and measure low current as well. But typically we find with high impedance devices, it's best to source current and measure voltage. That reduces your voltage noise, reduces some of your other effects. We'll learn some other techniques here in the low current and low voltage side, where you can can impact your measurements even further. But in general, sourcing current is the right solution here for these types of measurements. And this is how you can kind of see how those errors are calculated and where best to think about how to go after this device measurement. So yeah, so the important thing here is it's a combination of your offset and your gain error and your voltage noise on the range and levels that you've sort of chosen for your test. The other thing that's I think worth visualizing here a little bit is the sort of the ratio here, right? So how this compares in voltage space and current space, because I think that's important to just kind of intuitively visualize how you want to test a device. And right, so if you chart these error bands out as sort of a percentage of change, proportional voltage, proportional current, you find in general here, if you look at it as essentially a 1,000,000 to 1 ratio here, so you've got for each 10 nanoamps, you're looking at 10 millivolts, right? In this context, these SMU instruments are typically about twice as good at measuring 10 nanoamps as they are about measuring 10 millivolts. So you can see that by the divisions here of the error bands. They tend to be about twice as wide as they are high. So a little more noise and uncertainty in voltage space at the millivolt level than the nanoamp level, or at the volt level than the microamp level. So just an important kind of way to think about it to help you decide how best to test your devices, and just make sure you understand what accuracy you're actually getting out of them. And so if we do some tests there at sort of one of those middle bands, here we did a 1 microamp sort of 1 volt test connection, and you can see the types of accuracies and standard deviations you're able to easily get on a device like this. So you can see see that 1 second, a little small on my screen there. All right, yeah. So you can see the resistance in the main chart there. The resistance is in the blue line, and the current is in the green line. So you've got some, depending on environmental conditions and the instrument itself, you've got some current drifting at that's sort of sub nanoamp per division kind of changes in current there, but because you're measuring both the current and the voltage, the voltage is changing as well, and the resistance you're able to measure very accurately across that whole band. All right, so you're calculating small deviations, but you're able to stay very accurate in your resistance measurements for a device like this, with even a 1 microamp test condition that gives you accurate results down to at a very significant precision here, below really, again, standard deviations down below nanoamps. All right, so that kind of gives you, I think, a good feel for overall, how you want to approach a device test, especially in the resistance space, how you want to think about your source and your measurement, and how those accuracies sort of work together, how they sum together and create your uncertainty and your error bands. The next step really is thinking about some of the more complex setups. So now that we kind of understand how those resistance measurements are going to be made, and we've got an idea about what accuracy we can. Now we have to think about a few ways to improve the test conditions, the speed, and the accuracy in different ways. And one of those important configurations is pulsing. Right, so pulsing, we're going to see, allows us to do a couple things that are pretty interesting, and really maybe the most important here is just avoiding temperature changes in our device that affect its sort of measurement and affect its operating point, right, that we don't want to see. So when we do this, because of the complex sort of integrated setup here of an instrument like an SMU. You've really got the ability to fully kind of customize the all the timing here. So in this case, right, we're able to do pulses down to 600 microseconds. We're able to configure, as you can see in the yellow there, we've configured the measurement to happen right at the back end of that pulse, right? So after a settling time, after the current changes, we allow the current voltage to settle, then we take a measurement. Now, you can adjust all those delays and all those timings, and you can offset them. You can even move the measurement down to other parts of the pulse, depending upon what you actually want to see. But that customizability allows you ways to think more clearly about what you're trying to measure, what accuracy you need, what state you want the device into when it's being measured and ultimately analyzed, and that really helps you to get some different configurations here, right? So in this data set here, you can see we're able to get actually really tight millivolt measurements. Those are all coming off the top of those pulses at those are within sub millivolts for sure. There looks like. So we've got hundreds of microvolts of noise on those pulse measurements, but we're getting clear sign that the current is degrading over time, right? So that might be an indication that the pulse rate is too high on this device and it's starting to heat up, right? And therefore the current's reducing. Could be other impacts as well. Could be changing over time or other environmental considerations. But this is the kind of important analysis that gives you the ability to look at looking at those low currents, seeing those trends clearly with accurate measurements, and understanding the clear timing of those pulses gives you the ability to look deeper into your device physics and understand what's actually happening, whether you're in a sort of R&D phase here or maybe later even in a failure analysis mode. And so let's go one step deeper there and look at a couple different kind of timing and configuration sets up. So temperature and power sensitive devices here are one of the key areas because as we move towards smaller devices and new materials and new device physics, understanding how these operate over time, long-term reliability, temperature sensitivity, environmental sensitivity is an important factor in longevity and usefulness of some of these devices and different technologies. And so you might see pulse cycles like this where you have the current rising over time as maybe the device is cooling off. You've got or it could be trailing down, right? So these could be different configurations and setups depending upon your pulse timing, your duty cycle, your rep rate, and ultimately how you're making those measurements. But you're able to pretty accurately see those trends because of the sub kind of microamp accuracy. You're able to exercise with these types of instruments. Right. So we've talked a lot about ranging, sourcing, and pulsing. The next step in sort of the integration and measurement process here is really more about integrating these further integrating all these devices and all these sort of component tests together, right? And that's where I think it gets there's some interesting advanced tools and capabilities that you can use here, right? So we saw before we're able to synchronize those measurements with pulses, but going further with multi-channel systems especially, you're able to then now you can sweep those pulses. You can change as a list or as an arbitrary wave. You can change those pulse levels. You can change those voltage and current levels, and you have a number of trigger capabilities where you can integrate between multiple channels and multiple instruments to really optimize high-speed testing in a number of kind of stages of development. So here you can do pulse widths down as low as 50 microseconds. You have independent kind of ability to set delays, dwells, timing to really optimize how you want that measurement to happen, and you can coordinate between multiple channels very effectively. So if you need to do pulsing in parallel or sweeping and stepping, other capabilities, you'll see that can all be done with this sort of integration and optimization here. So really a graphic here about sort of how those triggers work with an instrument. But regardless of the source measure unit you have, you should have extensive ability to coordinate measurement, source, delay, and measurement activity across a pretty complicated trigger model across a number of instruments here. So that flexibility and that capability gives you other ways to address some of the measurement challenges you might see. And so here's a little test example that I think is valuable in terms of this kind of combination of sourcing and pulsing and sweeping. So actually here we're doing a pulsed sweep on an LED with a photoresistor on the other channel, right? And we're coordinating these measurements across a number of across both channels, measuring voltage and current all together. And so we set up that pulse sequence, and we really want to see how the current pulses, how they relate to the amount of resistance change and the timing on the photoresistor, right? So coordination of this sort of opto-isolated link, or this LED and sensor combination. And you can see you can see at the bottom here, the current bottom right, you can see the current as it goes up on that, as you'd expect to see on that diode, as we illuminate that LED, put more and more current out. And on the top, you can see the effect over time on the photoresistor, and how that resistance is changing relative to both those pulses and those peaks. Now, one interesting way to dig into this data and look at it in a different way is to combine this with an oscilloscope and use some of that integration and triggering to really get a combination view of the speed and timing of all these measurements. So here we did a sweep, pulse sweep of something. I think 1,001 points. Yep. So 1,001 sweep step here, and really trying to understand where that photoresistor starts to activate and how that resistance changes. So at the top of each peak with the source meter, the source measure unit, we're making measurements on the voltage and current on the source side into the diode, and we're making current and voltage and resistance measurements on the sensor on the photoresistor side, all simultaneously. Right? Now, if you monitor this and use the triggering to capture it with an oscilloscope as well, in like a sequence mode like this, this is a kind of a combined view of all 1,000 of those tests in the big window here. So you're able to capture. You can see that sequence of pulses coming up in the middle in yellow, and you can see the photoresistor effect in pink in the background there. And with an oscilloscope like this, and another way to combine this data, you're able to go through the history of each of these captures in the oscilloscope down on the right, looking at the history function, and you can see you can use this to find exactly when what voltage and current you need on the diode to really start to see the effect with the photoresistor. You can see the maximum effect, and you can see when it's having no effect. So you can cycle through all those images like a movie and consider all the impacts, right? So this is this kind of test would be a great way to do late stage design work or failure analysis on these links, right? Maybe you've got illumination leakage in other places. Maybe you've got electrical noise coming and it's causing you some grief. But being able to look directly at these measurements, both with spot measurements of high accuracy with the source measure unit, and simultaneously with looking at the timing and impact and accuracy of each cycle with an oscilloscope. So that's another way the sort of integration and capability of these instruments, I think, is pretty powerful from an analytic standpoint, and ultimately understanding what you're measuring and how you're measuring it standpoint. All right, so we're going to talk. We're going to go down for a few minutes here on talk about low current and low voltage, and some important aspects here, especially as you get down below, say, a nanoamp. Right? So most importantly here, this is sort of a picture here of a standard BNC cable, right? So you've got a center conductor, you've got insulation between that, and you have an outer conductor here, and you've got a resistance between the two, right? So typically a standard BNC cable like this is probably good down to about a nanoamp, right? But especially with a device like this where you might have high voltage up to 210 volts, you can get measurable leakage certainly down below a nanoamp of between the center conductor and the outer ring, and you might get environmental noise issues and other things coupling into your measurement from the outer conductor as well to the things around it. So how do we deal with that? What's the next step to make more accurate current measurements? And the real answer here is we have a set of there's a set of adapters and cables that we call triacs, right? So if you look at a cross section of that cable, you've got a center conductor insulation, a middle conductor insulation phase, and then an outer shield. And this is where we introduce a concept that is called guard, right? Or source guarding, right? So what this allows you to do is the instrument has a specialized output that is a buffered matching output of the high source. So if you think about this cable, and you've got your most sensitive, high source as at the center conductor, but completely surrounding that in the middle conductor is a guard. So that is always at the same voltage potential as a center conductor, and it's a buffered version of that. So now what happens in this configuration is because there's no voltage differential between the center conductor and the middle conductor, you get no current flow out of that center conductor. It's protected, it's guarded. So you have no current flow into the guard because it's always at the same potential. Now you still have current flow between the outer ring and the middle ring, but this really doesn't impact your main source, right? Because it's leaking current from the guard, which isn't part of the measurement path, and typically down to the shield here, which is typically outside of the measurement path as well. So you can use these cables, these triacs configurations with 3 conductors to really eliminate that current leakage, and you can earth shield these as well to eliminate the a lot of those environmental impacts, right? So in a complete configuration here, we might use 3 triacs cables to protect as you see in the graphic here, protect the high source, the high force, the high sense, and the low sense lines, with interconductors around them that are all at the same potential to eliminate leakage, and then all earth protected on the outer shield to really maximize your protection from both the environment and from other signals. So this is really the most complete configuration that allows you to eliminate as much current impact to your measurements as possible. And so once you're able to do that, you can then go ahead and take these measurements out to the DUT, right? So you can use a device like especially if you're on wafer or at a probing station, depending upon the type of materials or devices you're honestly testing, and you need to get down below nanoamps. You're able to, with the right kind of stages for your probe station, you can take those triax connections right out to the pin on the device, right? So they've got stations that allow you to protect from the environment all the way out to the pin level. It's a really great way to get your picoamp level measurements when needed, with a little bit extra care on your cabling side. Moving up from those from BNCs or shielded bananas up to a triax guarded configuration. And we can see that if we take a little data, we can see some of those impacts, right? So at the top here, you can see just the shielded banana jacks on an instrument with no cable connected. You can see where you're in that band, you're getting about 100 picoamps of sort of drift, right? That's about the offset range of these lower ranges. And you can see on the right, when you make a connection, right, you get a big current bump from coupling and triboelectric effects. But then you settle down and you get with a cable, just an open cable attached, you might get considerable current offset added from that BNC cable, right? Here it looks like about a nanoamp in this configuration. And then that same cable just sitting there really almost doubles the noise you're getting from just the banana jacks itself, right? So always be aware of impact your cabling and your cabling system and your environment can have, especially on your current data when you're starting to look at currents down below 1 or 5 nanoamps of measurement. And again, that being able to converting to a triax configuration or some kind of guarded configuration, especially for your high force and high sense measurements, is a great way to maximize the accuracy there. All right, on the voltage side, there's a couple of kind of tips and tricks for making these low voltage measurements that I wanted to discuss as well. This one's actually a pretty common one. You can see this in a lot of measurement systems. A lot of multimeters do this as well for standard 4-wire measurement, right? So obviously, what's happening here, just to be clear, right, is by separating the force and sense lines at the instrument, you're adding that series resistance of the cabling out to the device, and you have that in all 4 cables, right? But what's happening is all the current is flowing through the sense lines, or through the force lines, obviously, and it goes through this whole loop here. But because there is essentially no current draw from the high impedance sense lines, there's no voltage drop across these series resistances. So you can get really close to the device and eliminate some of the error from those series resistances by separating your high impedance measurement node here to the 4-wire. So essentially, you still have voltage drop across these force resistors, but you're no longer measuring across those. You're measuring across the other lines with very little current drop, or very little current flow. So that's how you can use 4-wire measurements to improve your voltage, essentially getting rid of heating, environmental issues, and cabling issues around your DUT using a 4-wire sense methodology. As you get even more advanced, one additional capability that's important here is offset compensated ohms. So again, when you're talking about resistance measurements and how to make them, and especially when you're talking about very sensitive voltage and current situations, right? A lot of materials or devices may have a base current or or an in-circuit current or some kind of quiescent current that's always flowing through that material, through that layer, right? And so the ability to make a good resistance measurement depends on your ability to eliminate that offset current or that offset voltage noise. And we can do that by integrating, really combining some of the pulse capabilities of an instrument like this with the resistance measurement capabilities. So if you envision a measurement like this, where we really have one resistance measurement, but we're doing it in two pieces. We do a voltage and current measurement essentially in an off configuration, and then a voltage and current measurement in an on configuration. And we look at the differential, the changes in the current over the changes in the voltage, and that gives us the accurate resistance measurement is the differential voltage divided by the differential current. So here we have, so that's a great way to really get a little further and eliminate other environmental issues or fixed currents and voltage that are impacting your system. And so, with a measurement like this on a low resistance device, around 30 milliohm, right? You can drop that noise down to 20 microvolts peak to peak fairly easily, right? So really getting down towards true microvolt measurements with proper measurement technique on the low voltage side. All right, wanted to really just go through as we've kind of talked through the main capabilities. We've talked through some of the tips and tricks on ranging, sourcing, pulsing, and coordination. Gotten through sweeping, and so wanted to take a few minutes and just talk about the last set of now we're talking about really complex devices and how we can really use those tools to optimize some of the measurements around some of these devices we want to look at, and some of these characterization tests we need to do. And we're going to look at really kind of take a quick look at sort of four devices here, right? Diodes, batteries, some transistors, and solar cells, and how these work together to make these measurements. And the first, I think, most important characteristic we talked about briefly off the top is this 4-quadrant operation, right? So your ability to switch from sourcing and syncing current and voltage on the fly while making critical measurements really allows you to get to a broad set of devices. So here's a couple looks at a diode, both looking at the operating range down through the reverse breakdown. Right. So again, you've got much different current levels here, many octaves, many decades of current from milliamps down to nanoamps as you approach zero and get into a reverse breakdown. So you have to be careful how you set up and analyze this data, but your ability to get that whole cycle of data in one sweep with powerful measurement capabilities on the right ranges at every step is important. And for 4-quadrant work, it's obviously that your diodes typically will break down here in what we call quadrant 3. We're going to talk about battery charge and discharge cycles, which typically in quadrants 1 and 4. And how we use this operating capability to look at how solar cells and solar modules might work as well. In terms of battery charging and discharging, right? You have to be able to monitor these very low currents, right? You might be whether it's a big battery or a material test, a research level. Looking at new battery chemistries or other things, right? Being able to trickle charge and discharge these batteries at low current is impactful. Being very careful with temperature, charging and discharging with really complicated sort of current, voltage, and time parameters allows you to monitor and manage temperature and chemical processes within the battery, and so all that's really important to both characterizing and finding really the best use cases and operating modes for complex battery chemistries and setups. So systems like this would also allow you to monitor them, with larger systems in parallel, higher voltages and higher current. Use the pulsing, arbitrary mode, and duty cycle characteristics to really manage your entire system here the way you need, and ultimately get really accurate data once we've measuring it correctly on either the both on the voltage and the current side, giving you the best look possible at your efficiency, your charging cycles, your reliability, and your operating modes for these kind of battery physics. One other thing that the coordination and close automation setup, especially when you're talking about multiple channels or a parametric system here with multiple source measure units, really allows you to do is you can now do combinations of sweeping and stepping or biasing across different points on a complex device, right? So here's a sort of standard view of what you'd expect from a family of curves from a transistor, right? Being able to do that all within one box with two channels, while stepping the current. You can combine pulsing, you can combine sweeping, and you can trigger and automate these all together using a combination of internal and external triggers to really get both speed and accuracy out of multi-channel devices, whether it's a transistor or a more complicated setup with multiple channels and very low voltage or low current needs. Right, so sequencing, synchronizing, and working together with these careful timings becomes an important aspect to a lot of these complicated device challenges. And one kind of, as we get towards the end here, one last device I wanted to look at and talk about for a second is in the photovoltaics area, whether it's a solar cell, a module, new physics or chemistry you're looking at. When you're building up a device in a research phase, right? Your ability to kind of monitor, look at illuminated cells and how they're delivering power, and talk about their power and efficiency is an important aspect. And so here we see sort of the traditional IV curve of a simple solar cell, and it's important to note that really key measurement aspects of that really require your ability to complete the quadrant, right? You have to be able to go all the way down to or test all the way down to a short circuit current, test all the way over to open circuit voltage to kind of simplify those values so that you can then calculate the max power on the curve, and then the fill factor. So fill factor for a solar cell is really a measurement of efficiency, and it's really the ratio there of the max power under certain illumination conditions versus the product of the short circuit current and the open circuit voltage, right? So your ability to fill that square, if you will, is the fill factor, and in a lot of important ways and some newer ways to test and verify efficiency of these cells and modules, but they all really require both typically accurate voltage and current measurements across an entire quadrant, and sometimes into additional quadrants as you look at and make these measurements. So another important device here, and worth knowing that this graphic here is typically shown like this, right? But it's actually happening from the instrument's perspective in quadrant 4, right? Because this device is delivering current to the instrument. So the current sees that as negative current at positive voltage. All right, so that was really the devices I wanted to talk about. So, obviously, in addition to some of the ways we can make these measurements, some of the tips and tricks for monitoring accuracy, getting better accuracy out of low current and low voltage measurements, and using these for complex devices. Part of that key is your visualization and how you want to visualize and analyze this data, right? And so, proper source measure unit gives you a lot of capabilities to do that today, whether it be on screen with graphics and roll modes and data visualization there with a touchscreen through a web browser, or standalone software that allows you to pull and configure that data and save it offline for further analysis as well. So you should have with whatever source measure unit you work with, you should be able to get that accurate data out for analysis in a number of easy ways, and you should be able to program that directly in things like LabVIEW and Python if you prefer. And so that really brings us to the end of the day. Keep a lookout for new information as we're here at SIGLENT are about to launch some new source measure units. So we'll be sending that information out over the next couple of weeks here. But really, just wanted to thank you all for coming and talking a little bit about how we make these measurements and some of those key factors and tips and tricks as we move towards some new instruments on the horizon and new capabilities. And that really brings us to the end here.
All right. Well, thank you, Chris. That was really a master class in how to use an SMU. I really appreciated that detailed discussion kind of early on about ranging and accuracy and the interplay between those specifications. But yeah, just in general, a great discussion about best practices for using SMUs to make some really difficult measurements. So thank you for that.
Thank you.
Yeah, we've already got some great questions from the audience, but I remind everyone that there's still time to submit your questions for Chris. We've got a few minutes to go through some, so just type them into the Q&A section on your screen, and then keep an eye on that handouts tab. We'll get the slide presentation available shortly. But Chris, let's jump into our first question. What's the biggest difference between using an integrated SMU versus a system consisting of supplies and meters to replicate the power?
Yeah, great. So I think the real advantage, and we talked about some of this, right? The real advantage is the ways these are integrated, both in a digital sense and an analog sense is important. But really, I think focusing on the analog side is sort of critical. Your ability to get to those lower level measurements, low current and low voltage, is really a product of how the integration and protection circuits are done to give you this really highly integrated but still very accurate measurement. Right? So what you lose mostly by trying to build a system yourself to do some of these measurements is accuracy and speed.
Sure, that makes sense. Yeah, and when you're talking about microvolts and picoamps, a non-integrated system, those problems are just going to get worse.
Yeah, absolutely.
Yeah. What industries use this type of SMU technology in today's applications?
Yeah, so I think source measure units are broadly used across a number of areas and industries, right? So I think you see them a lot in some materials research, right? Whether it be kind of nanowires or MEMS, especially on the combination of the high resistance and the low resistance, right? So your kind of superconductor research, I think at a materials level, these become important tools. You see them a lot in really parameter analysis for complex semiconductors. Some of that's at a fab level or on wafer, but it can also be at a device level. So some of it's used as for batch or bin testing. For some of those complex devices as well, and I think you do see a lot of them in sort of a combination of new energy, whether it be battery test or kind of solar work or generator work, and then automotive, right? So traditionally there's a lot of connectorization, highly reliable connectorization requirements on today's automobiles. Right, so you've got all those buses running and all those sensors that are sort of hypercritical for long-term use in corrosive environments, right? And so you tend to do a lot of impedance and resistance testing under different circumstances for those kind of devices as well. And I think that ultimately leads towards a pretty broad set of sort of mission critical connectivity kind of measurements.
Sure. Yeah. Excellent. Next question. What are the most important considerations when trying to optimize for low current accuracy?
Yeah. So I think as you move lower and lower in the current regime, this is where like measurements become pretty challenging, right? And one of the ways to best optimize it, we talked about some of them, right? I think environmental and cable interactions are critical aspects, right? To get below a nanoamp, you really start to have to care about those. You have to care about your cable materials. You start to worry about vibrations. Environmentally, you start to worry about electric and magnetic fields nearby. So also you're we didn't really talk much about fixturing, but however you need to make that device measurement, right? Making sure that you've eliminated environmental impacts, while also hopefully not causing a lot of ground loop type issues, is important, right? So that combination, I think, is where you see a lot of those measurements being made, and where they get kind of tricky. But using these techniques, right, combination of the cable techniques and some of these differential offset measurements to try to get rid of and tweak out those offset values to get the most out of your measurements is I think where the magic is.
Yeah. I like this question here. It's that how can SMUs work in complex systems with other test equipment? And, what are the kind of the keys to successful use in these system applications?
Yeah, great. I think we did a little bit of that today with combining it with an oscilloscope to give you a different view of some of those measurements. But source measure units are again are kind of critical system components and system applications, right? So you use them with high speed pulse generators, wave generators, measurements. In a number of different varieties, obviously, because you're typically measuring power and battery consumption here. There's a lot of RF capabilities as well, right? So you might have a RF amplifier circuit, and you want to see how its power requirements in different configurations and in different temperatures and under different circumstances as well. So you can combine these with network analysis and signal source instruments as well. So, because it's essentially, typically tied closely to either, some of the nonlinear behaviors of your devices or power measurements, I think you get a lot of integration and a lot of measurement requirements really across the board, with everything from, high speed scope measurements to high frequency RF type measurements.
All right, well, let's squeeze in one more question here, Chris, before we hit the top of the hour. And it's like a two-parter. I think I'll take the first part of this. What advantages do the SMU's versatility bring to research applications?
Great. So, I think research is one of the more interesting applications here, right? And we see it a lot at universities and materials labs. Whether they're on the nanotech side or other areas, right? Your ability to make accurate measurements in these complex environments, whether it be on a wafer or on some kind of other substrate where you've created or tested or built devices, and you don't really know what they're going to do, right? You're trying to figure out how to make something more useful or better. That's where the breadth of capability really, I think, becomes powerful, right? Because you can take an instrument like this and you can do high power pulse measurements. You can dial that back and make the same measurement at really low power. You can look at it at low voltage and make differential measurements. So depending upon your as you build out new test hypotheses for these devices and materials you're making, you really have a broad range of ability to test, monitor, and analyze things from super high impedance to really quite low impedance, right? So you got a great breadth of gear for a lab to do all kinds of testing, and really you have the customization to be able to do it in a bunch of different ways.
Well, excellent. Well, Chris, thanks again for the great presentation and the discussion during the Q&A. Glad to have you today.
Thanks so much. I appreciate it.
And thanks to everyone in the audience for your participation and joining us. Everyone, in just a moment, you'll be redirected to SIGLENT's homepage for more information. Also, be sure to check out SIGLENT's author page on All About Circuits, where you'll be able to view this session on demand. Thanks, everyone, for your time. We look forward to seeing you at another live session again sometime soon.